Yeah, it is. Kind of rough on the engine.
Yeah.
When you have a surge, an engine surge, as it's officially known, that all goes down in the flight data recorder. And the pilot it's on the pilot to be sure they tell the maintenance people that they've had such a situation, because in that situation, that means going in with a borescope and looking the engine over to make sure nothing's bad or out of place. And pilots sometimes don't want to say anything about that. Because it kind of, the icky gets on them, and they don't want to admit to it. So, but it is important that these engines get inspected when they have an engine surge. Now, I suspect on the C-17, it's not anything that's uncommon, given that they're back in the airplane using the thrust reverser. As soon as you degrade the airflow across the inlet here, that then lowers the pressure on an engine that's running at a fairly high rate of speed, and so you end up with a situation like that. Looking for my marker here. Gosh, I stole my marker. Another color. Okay, so you have that cascade effect where the pressure starts to build first slowly, and then all of a sudden it starts going like this. Well, that also, as that pressure builds like that, the RPM of the engine builds like that. But if you have a situation like this, where at some point in the middle, kind of goes like this, and then goes back up again, this bubble follows all the way up, all the way through the engine. And when it does that, you have that momentary loss of pressure, and that gas is looking for a way out. Okay, so there's methods of balancing that compressor pressure ratio. So they may derate different stages on the engine. So when they build these engines, they're looking for optimal pressures, and they have kind of in their mind what they're looking for, but it can be adjusted by changing the angle of attack on the front stages, or the amount of air that the blades are moving in. They can use bleed valves. If the pressure gets too high at the back of the compressor, if it gets too high back here, all they do is they put a bleed valve in here, or maybe one in here, and if it gets too high in a spot for any momentary reason, it just dumps that air overboard and allows, and then it will close again very, very quickly and slam shut. These things all have what they call muscle lines on them to operate them. They're nothing more than dump valves. They open up, allow air out, and then they close them again. So these things sometimes will sit there and kind of flare and hop on their seats, but then they'll slam shut again. You don't want any air escaping if you get away with it. So they'll install bleed valves to allow air out. And that just temporarily lowers the internal pressure in the compressor. They may also split the rotors into two rotor systems, or two spools. And that gives a little bit of float between the front stages and the rear stages. So if the front of the compressor starts turning too fast, it's not going to make the rear of the compressor speed up real rapidly. The rear of the compressor will be able to catch up at its own speed. So I got a couple more acronyms here for you. I'm not going to talk about those today, but we'll talk about those toward the end of the semester, because it starts getting a little bit confusing. So VIGV. VGB. Variable inlet guide vane. Variable guide vane. Put these in your acronym book there. What they can do is usually the first several stages of the engine. They have some vanes, stator vanes in there that can pirouette, they can move slightly. We can use those to block air, or we can use them to allow more air to go into the compressor. So we can turn those, and they're set up, it's scheduled, not by the pilot, they're set up according to the fuel flow and the throttle lever angle. They also use a variable area or aperture on the exhaust nozzle to either load or unload the compressor. Remember, the engine operates on the difference between what goes in to what goes out. And if we change what goes out, that's going to change what goes into the engine. Or you can use any combination of those. And in a lot of cases, they do use all of those things simultaneously. So the axial flow designs, we have a rotor section and a stator section for each stage. The construction is going to include an external compressor housing. It's going to include seals. Some of you, there's one group of you, I'm going to start on seals tonight. Air seals. Stator blades. Now if you think about it, as you go back through the compressor, you have pressure building through each stage of the compressor. Along the way, you don't want that air to escape from stage to stage. You want it to go from this blade to this vane to the next blade to the next vane, right? If you start having it escape around the tips of the blades, then it's not going through the blades. Then you lose efficiency. If it escapes at the base or the root of the blades, it's not going across the next blade and vane in sequence. And so if it doesn't go where it's supposed to go, you're losing efficiency in the compressor. So what's going to happen is they put seals in there, air seals. And we'll talk about those down the road too. But these air seals are critical to making sure these things operate correctly. Also, you don't want to have anything that leaks to the outside world through the case. So where the cases are put together, there's usually some sort of an overlap or a fish mouth between the cases that fit together so that air can't escape out through the case. They also make sure that the bleed valves close correctly. If the bleed valve doesn't close correctly, you've lost air from the compressor. All of these things combined to degrade the efficiency of the engine. So they're pretty commonly assembled on discs, the rotors, tied to each other, or it may be a tube that they're all attached together on. The stators may be assembled in partial circumference shells, that is to say halves or clamshells. One half goes around the other half, fits around the rotor in the engine. This just makes for ease of assembly. So the compressor and the turbines may very well have a containment ring on them. So if something is liberated within the engine, there's a very good chance it goes straight back through the engine instead of and out the back, instead of going through the wing or pressure vessel, fuselage, any of that. Doesn't always work, but quite often it does.
You'd rather have it there than not. That's what you're saying.
Exactly right. Yeah, there was a going into Honolulu, I think it was a couple weeks ago, by United, and it lost the whole inlet assembly. Tore the fan cowl off the engine. What happened was the fan broke and tore the whole front end of the engine off. And it went back, as near as I can tell, it went back up and over the wing. Didn't do anything it was supposed to do, but at least it didn't hit the aircraft as it went away. Okay, so there's some tests that these things go through for certification. And now these engines they're double expensive. I mean, these things are $100 million for these freaking engines. And so they don't just destroy it idly. So they do a lot of testing on the engine. When it gets close to the end of its testing cycle, then they start doing some of this destructive testing on the engine. So I'm going to show you, they're going to put water in there, rain, to simulate rain, and a lot of aircraft fly through monsoon conditions. They're going to simulate bird strikes, and they're going to simulate a blade coming off of the fan. So let me turn the lights down here. So we'll just watch a couple of videos. That's interesting. If you want me to replay, I will. Oh, great. Okay. Well, we'll find it. I know it's still here. So let's see, I want to do this. Here. So, let me tell you this before I show this to you. Those blades, those blades are, each one of them is about this tall, with 4 feet and change wide or long. Now these are all made out of titanium alloys. A lot of these blades are made out of composite materials. And so they're all just about the same weight, but they're all tougher than hell. Turn some sound on here. So I gotta go back. So that one there's gotta go plus. Yeah, here we go. Okay, so let's start with silver. We got updated here, which makes it doesn't work anymore.
Nottinghamshire. Another test engine will soon be a smoking ruin, deliberately destroyed as part of a dramatic and crucial safety test.
So they have a big tube that goes across to the center of the hub, because they don't want this thing ended up on the parking lot. So all it is a
She
safety
admits to
device.
some nerves.
Honestly, I got a few butterflies at the moment, but basically everybody's done the preparation and it's just now a matter of getting on and doing the test. Obviously before the engine starts, you're sitting there just kind of hoping it all go well, but just really waiting for it to happen now.
Every few years, a fan blade will fail in a jet engine somewhere in the world. A rare but violent event that must not put lives in danger. At the root of the coloured blade is an explosive charge. With the engine at full power, it will be detonated, releasing the blade with astonishing force. Whatever happens, the blade must not be allowed to burst out of the engine, where, in real life, it could do serious damage to the rest of the aircraft.
I picked this one so that it just speaks Swedish.
In a room 200
Practicing.
yards away, watching via a video link, are 25 key personnel, each hoping the test goes as planned. In the split second the blade is released, the engine must successfully contain an enormous amount of energy.
It is a very violent test. This thing is spinning round, it's at full power, so you've got the forces on the blade are quite significant. It's like having a locomotive hanging on that blade. So you're actually having to contain the energy of that system. So there's a lot of energy involved in the design and containment of the blade. I mean the whole engine will get a huge big shape.
As ever, the size of the A380 increases the challenge. The bigger the engine, the bigger the blades, and the greater the energy released if one were to fail. Spinning at 3,000 revolutions per minute, the blades experience a force of more than 7,000 times their own weight. So everything is done to make them as light and as strong as possible. A top-secret process molds the blades from ultra-strong, ultra-light titanium alloy. To save further weight, the blades are heated to 900 degrees in a furnace until they are softened. The gas is pumped into cavities inside the blade, inflating it like a long, thin balloon. The result is a hollow part curved in 3 directions for aerodynamic efficiency, supremely strong, yet light enough for someone to pick up and move quite easily. Each one costs the same as a luxury car, and a full set of 24 are about to be destroyed in the name of safety. As the critical test for the Airbus A380's engine gets underway, it's run for 5 minutes at low power, so final checks can be made. The main concern is that as the blade is blown free, the casing around the fan absorbs the huge impact and prevents potentially lethal shrapnel from escaping. High-speed film cameras are used to analyze the action, and at last, the throttles are opened and the engine brought to its full, awesome power. This is what it feels like to be inside a building 200 yards away from a £9 million blade-off event.
see the fire coming forward through the engine there. That's the compressor. Allowing lost pressure because the blades come off.
Blade off testing is normally top secret, but for the first time, Rolls-Royce have released this footage. Although the engine was totally destroyed, the fan case did its job, and no large lumps of metal were ejected. For Hilary Barton, it's been a good day.
I feel very relieved. Obviously, it's gone well. Had a good test, and all credit to the guys. And yes, we've got a successful test under our belt. So I feel relieved and.
Where goes your profit share?
As the critical tests, the casing around the fan absorbs the huge impact and
Go
prevents
through this again.
potentially
You
lethal
saw that the
shrapnel from
parts go
escaping.
through the engine. It's like a snake swallowing an egg.
High-speed film cameras are used to analyze the action, and at last, the throttles are opened and the engine brought to its full, awesome power. This is what it feels like to be inside a building 200 yards away from a £9 million blade-off event. Blade-off testing is normally top secret, but for the first time, Rolls-Royce have released this footage. Although the engine was totally destroyed, the fan case did its job, and no large lumps of metal were ejected.
You see how fast that combustion gas will come forward as soon as you decrease the pressure in the front of the engine. All right, as long as we're here. So some of the other things that that the engines go through is bird ingestion. And if you like birds, you might want to look away a minute.
Well, use frozen chickens. It's nothing to cry over.
Yeah, I should say. I'll tell you the story. So I did a lot of work for Pratt Whitney, and the joke around there was at one time, Rolls-Royce said they called up Pratt and says, how do you guys do that? We're really tearing these things up, shooting these birds in there. And so the Pratt Whitney guy apparently told him, he said, well, you're not using frozen birds, are you? And the guy says, oh, yeah, well, we buy them down at the grocery store, you know, and because they have a cannon and you shoot them into these things. But the guy's just shaking his head. You don't use.
They don't thaw them out.
Don't use, they weren't thawing them out. They were shooting them right in there frozen.
Well, it's like a rocket size engine.
Yeah. This, you're just going to see hair, teeth, and eyeballs coming out the back here. But they shoot them in there. It's like a giant Cuisinart.
Barbecue.
Yeah, just like a big Cuisinart. They come out of a pneumatic cannon so that they go where they want them to go. So they put some in around the booster, which is near the splitter there, and then the rest of it goes out through the fan. So they just want to see how the blades react. But you can see the flexibility of the blades there. I'll run that for you again.
It's edible that comes off the back. Yeah. It's edible.
It needs to be heated in the combustion chamber. So
Once it comes out the exhaust duct,
So,
though,
so
it's
watch,
ready to
watch
eat.
the
there
fan.
you go.
Arms and table.
Watch the fan, and watch the blade deflect when the bird's hit.
And it looks like it's bounced back.
Yeah, they'll bend back and then they spring right back forward again.
So are those blades?
So those blades are they're hollow, as you saw. Let's go back here. They're hollow. The blow them up in a mold, and then they're edge vacuum welded.
So do they do like bigger birds or more of them at the same
Yeah,
time?
they do everything from chickens to ducks to geese. Yeah, they'll use just about everything.
That will throw a cow.
That's
beautiful.
As long as they get the good parts.
Chicken gun. It's like underwater.
Chicken gun.
Here's the chicken gun, the famous chicken gun. We're getting a little twisted here, but that's
Wrong. That side of YouTube again.
That's a lot of birds they're firing in there.
There's
It's
like some
6 different birds.
So what'd you do at work today?
yeah.
Shot dead chickens
That's
with
why
a
we
jet
go to
engine.
Costco for chicken.
The number 4 chicken.
Do you put that on your resume?
I like when we showing the slow-mo of chickens coming out. That's
Yeah.
awesome.
They're not too slow, but they didn't want to show the chicken screaming, but. All right, so they also have, oh, geez. What else? Water. Water's another one. Water's really hard on an engine. And it's nothing more than kind of just backing up a big spigot to the inlet and feeding the engine water. Because there's certain parts of the world where, let's try this water ingestion test, where these aircraft land. Southeast Asia is a good example. Where they'll land the aircraft. I know I was riding in Hong Kong one time. Boy, it was a beautiful day. It was just drop dead gorgeous. And then all of a sudden you get these squalls, and you go through the water and you think somebody just observed the sky. And so they have to test these to make sure that these engines will continue to run even though they're swallowing
Recently,
millions of
Boeing
gallons
completed
of
the
water.
first flight of the GE90-115B powered 777-300ER aircraft. The GE90-115B was developed by GE Aircraft Engines exclusively for the 777-300ER. The GE90-115B engine delivers 115,000 pounds of takeoff thrust to the 300ER and represents the highest thrust jet engine in aviation history. Key certification testing was conducted at GE Aircraft Engines outdoor test facility located near Peebles, Ohio.
I'm doing 837, begin icing cloud.
The 952-34 on point, continue around storm for 30 seconds.
3/4 of the time.
We'll total water flow of 1100 GPM. Water on for everything. Water. I don't know if this is. Row 637.
4.5 miles per minute.
Takeoff.
Just a little bit.
That's just a little bit.
Happy with that, right? Just moving fast.
There are blades missing. They want to destroy as few blades as possible.
Right?
Delta, runway 30, wind column, clear for takeoff. Godspeed.
One of these engines is not like the other.
It's really weird.
Yeah, it's kinda close, huh?
Little bit.
Curb feelers on that.
Time is 23:57. We'll start change at 51:46. Axle or triple red line. Axle now.
And you know he drives a truck.
Yeah.
Triple red line.
Time is 0001. 1 point, triple red line. Take ABS 187. Clock 211. Fan 2617. Core 11,321. EGT 2013.
$121,000 of thrust.
Both the
GE90
aircraft engines.
Not exactly the newest engine on the fleet anymore, but still,
Safety,
still used
comfort,
on,
and reliability.
on brand new airplanes.
Let's just say, I'm trying to say. No kidding. First one with birds.
No.
Oh, right at the punchline. Okay. All right, so you kind of get the idea.
Yeah, it is wicked.
Recently,
There's a ton of these on YouTube. I invite you to take a look. It's all good stuff. It's interesting stuff, and I'll use their information frequently. As I say, you can learn a lot off of these company videos. Of course, you know their stuff is better than everybody else's, so you have to kind of measure that in there too. Okay, so we did that one. We did that one. Okay, we did that one. Okay, so we go with this, did that. Containment ring. Okay, so this is the blade off test. Okay, so here. I want you to see this one here.
Almost the 30.
Somebody caught this on airplane was on takeoff, and the takeoff roll. What do you imagine happened there?
Acclimated.
What do you imagine was going on there?
Something catastrophic.
Something bad, very bad. Okay, so what would you guess based on what you just saw?
The merge charge.
Well, I'd say blade off.
Probably a blade came off this thing. Yeah, you got so much fire coming out of it, and you have a lot coming out the back, but the back part is what already is come forward and gone back through the engine. So you're still seeing the glow coming out of the combustion chamber. So that engine is at full throttle, and it's being fed a lot of fuel, and that fuel just continues to run into the combustion chamber, but there's not enough air being forced into the combustion chamber to hold that stuff in place. So they got the airplane stopped, as I understand it, and got everything shut down and extinguished the fire. But typically aircraft components fail, not in their steady state, but on acceleration and deceleration. So this is the perfect time, and the pilots and the crew are looking for this to happen. So they did what they call a rejected takeoff, and lowered the nose, stopped the airplane, and everybody. Of course, most of the passengers probably never even saw it because it's like kind of hidden under the wing. But this is, as I understand it, was taken from the control tower.
The screenshot then has video or something?
Hmm?
Screenshot has video?
Screenshot out of the video. Yeah. All right. So we talked about the stator vanes. When I told you about those variable inlet guide vanes and the variable guide vanes, they pivot along their span. What that does is it changes the relative angle of attack. So if you open the throttle too quickly, that destroys the pressure zone around the stator. So what you can do is, and the aircraft knows when it's being accelerated too rapidly, and they know what the pressures, the engine knows what the pressures are within it. What it'll do is it will just move the angle of attack to compensate for the increase in the airflow. So every stator blade in that stage will just turn, and it might only be 10, 15 degrees, some of them may be 45 degrees. Okay, so the rotors, they're made out of stacked discs with blades attached. Right there. They're attached to central hubs. And the blades are attached with a couple of root designs on the blades. It's not the airfoil portion. They're called fir tree or dovetail. You should put a little gold star next to those, because the FAA, I looked in the test guide for the last 10 years and they're still asking the same question, so know that you're gonna see that. I'm gonna show you the fir tree and the dovetail designs, the difference between the two. There are some other designs that each engine manufacturer uses on occasion, but they all kind of come out of the fir tree or dovetail design. Okay. So if you kind of stand on your head, the one on the left looks like a Christmas tree or a fir tree. Okay. The one on the right looks like the tail of a dove, hence the name dovetail. Now the reason they use these is so that the blades can move around just a little bit. They're not locked in solid in place, because you want them to be able to wiggle a little bit. You don't want them to move around a lot. Once you get centrifugal force acting on these, they lock themselves up solid. So they still have some room for a little bit of motion. The temperature is going to rise inside the compressor, and when it does, these things are going to try to tighten up. But you don't want them to lock up tight. Only want centrifugal force to cause them to lock up tight. So these things still are able to move a little bit around because of the changes in the temperature in the attachment. So you'll have 80 blades attached to a wheel, and they'll be attached with either a fir tree or a dovetail design. Now this more often than not, they use a fir tree on the turbine blades, but they'll use some similar arrangement to the dovetail, also on some turbine blades. So they allow for control of heat. So the blade's going to expand faster than the wheel. That's why you have to have a little bit of wiggle room in there. Allows the blade to expand into the slot that it's mounted in, and also allows them to move a little bit. Once they begin to turn, they lock up. Again, we use these for compressor and turbine blade retention.
So are these blades, what kind of material? What kind of? It's not composite.
Compressor blades usually are titanium anymore. The turbine blades usually are high nickel steel. Okay, a lot of times they're made by investment casting. Most of the time, they're machined and forged. And most of the other drive machinery is forged steel, high nickel forged steel. So the nickel helps prevent corrosion. It's also stronger with the addition of the nickel alloy. How do you know what investment casting is? Anybody? Investment casting. So I throw this stuff out there, and stop me if you don't know what this stuff is. So investment casting is, look around. So if I wanted to make one of these out of metal, what I would do is I would take this shape here, and I would carve out a little bit of a mold, and then fill the mold. But that's kind of expensive, because you have to have a lot of molds, especially when you have as many blades as you do in a compressor. So what they do is they take a model blade, and then they cast it, or they surround it with a ceramic material. And they make that mold, the original piece, out of wax. So every one is the same, just the next to the next to the next. So you've got all these little wax, these. You surround it with ceramic material. And then what you do is you heat it, because it's a ceramic, you can heat the ceramic, and the wax burns out. That leaves a cavity behind. And then you add the metal to it. Well, that way every one of them is the same to the next, to the next, to the next. You don't end up with any differences between them. You don't have to have 50 blades, so you can make enough of these things to have 50 different molds. So every one of them is identical to the next. You all see how that works? Mm-hmm. So I make one of these out of wax. It's called mold wax. Make one of those. You put ceramic. You dip it in a ceramic material. And then you heat the ceramic material, not only to dry the ceramic, but also to chase the wax out, because now you're going to melt the wax out. Wax comes out, just burns right out of there, and leaves an empty cavity this same shape. You just pour that material, pour the metal into the ceramic mold, and they're all the same. They call it investment cast because you take something, you make an investment in this little piece here, and you throw it away. But you use something that's fairly inexpensive and throw it away, instead of having to generate a lot of molds, each one of which is a little bit different from the next. So, assuming all of these are filled up, all of these little ceramic molds are filled up the same way, every one of these weighs the same, every one looks the same, they all fit, form, and function the same as the next. And so you end up with a complete set of blades. The other good thing about this is what they call the net. That means the amount of machining that you have to do left over means that you don't have to hardly do any machining. When you break the ceramic away from the mold, from the part, you take out the part, because they're all the same, you just put them right in. You don't have to monkey around with running them through machine operation. So you save a lot of time and money that way. Okay, so forging is going to provide greater molecular alignment and strength. Casting is better for detail and complexity. When you forge a part, you can still machine it to get the detail out of it. But that's another operation, and that starts costing you money.
Can you explain like what you mean by greater detail?
Sure, the shape of the part. So some parts have little fancy little nooks and crannies and corners in them. So let's say a compressor blade, use that for an example. You don't want air to escape past the blade, right? So we talked about that. So you may want to have a platform at the base of the blade. So the blade stands this high, but at the base of that blade, you may want to have a little square of metal there that will interlock with the next blade. It's the next blade, it's the next blade. So that provides a zone where the air can't escape past it at the base of the blade. The tip of the blade you don't care so much because you're going to have a braidable liner for the tips, and that's going to create a zero clearance on the tips, which keeps the air from escaping over the tips. So anytime you add a little bit of extra on the blade, now that's detail, and that adds to the cost of the blade. Okay, so blade inspection. What to tell you, if you ever go to work someplace and they offer you a job in the rotor and blade inspection area, you probably, think twice about it, because it's an inspector's duty typically. It's a lot of blending. How many enjoy blending? Me? I didn't see you. Oh, it's two of you. Okay. Two. All right. Some people, it's their thing. But once you've done your first box of blades, your first 80 blades, you're probably not going to be so excited about it. I can tell you it's boring as hell, having done it. All right, so the checks you're going to make, first of all, is for damage. And then you're going to be checking the cord on the blades and the span to make sure they're long enough. If you have enough cord on the blade, then you'll have a scrap box, and you throw the ones that don't meet the criteria into the scrap box. You also check them for a pitch angle or blade angle. And there's a little, looks like a mold. You just fit it into the mold. If it tips, doesn't fit correctly in the mold, that means it's been twisted somewhere along the line. Blades get twisted occasionally. A piece of like tire rubber goes down into the inlet. Gets stuck in there and bounced around a little bit. It will twist the blades. It won't just break them. A lot of times it just bends them. So if you bend the blades, you're also scrapped. Then there's going to be the NDT work. So you're going to start with visual, and then it'll probably go to eddy current. Eddy current is going to check to make sure there's no cracks in the blades. Any internal failures. And each blade, in turn, is going to have to be checked. It's quite a lot of work in that. It's a full day's work to do one engine. And any blending that may have to occur as well. This is usually carried out by several people. You have some people that are NDT qualified for different tasks, maybe eddy current, dye penetrant and Zygo inspection, all of those things, X-ray, all of that. So you'll be working with quite a number of different people. Like I say, after you've done your first box of blades, you'll probably wish you were working somewhere else. There's usually a little premium goes with it though, because it is kind of a boring job. Yeah.
So with stators that are fixed to the clamshell, how do they fix those?
They
Are
pull
they
them out.
movable?
Yeah,
They are
they
removable?
detach. Yeah, they come right off the shell. Yeah. So the shell is not formed with the stators, not machined part of it with the stators. They're attached to it. Usually they're welded or bolted. Okay, so fan blades. A little project out here for some of you on fan blades. They have what they call an inner span or a mid-span shroud. And what that is, it's a support. So each one of the blades, of course you can't hear it anymore. I used to go down to the airport and see the wind blowing through the engines, and the engines would be turning, and you hear this clink, 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 clink as the blades, as they rotate around. Well, what that does is there's a certain small amount of movement in the blade when the engine is running very slowly or turning very slowly. But as soon as the speed of the engine picks up, the blades, as they're trying to grab the air, move forward. And when they do, all of these mid-span supports interlock with one another, and the fan then becomes one solid disc. And so this can be an area where there may be some damage also. So they can also, if there's an engine surge event, it may also cause the blades to become shingled. So you all know when you put tiles on a roof, they all kind of, as you go down the roof, they have to be overlapped one after the other, right? Well, if there's a surge event, what happens is it blows all the blades forward, bends them, and then you end up, instead of having your shingles like this, you've got one that's over top of the other, and it blocks up the set. Causes a lot of vibration on the engine, and it can actually break the blade. The other thing can be called a shackle. And that means if it's locked up, you have to take the fan set out to get that blade out of it. As you all get to my fan project, I'll explain that too. Okay, so water ingestion, you already saw that.
So Lonnie, can I ask you about that a little bit more? For airplanes that operate in Asia, that's a typical condition.
Yeah, monsoon's a big deal.
So how do they deal with that?
They just ingest the water. They try not to, you'll see them, Hong Kong, Kai-Tak, the original airport there, used to fly straight to a mountain. There was a big, like a bullseye on the mountain. And then once you got, because what happened is you flew toward the mountain. I'll show you. It was really an interesting arrival. And you kind of had to talk to yourself, as I understand it. I was in the jump seat when I did this. So you fly to this mountain. It's just kind of this big mountain out there in the bay, and it had like a big bullseye. So you did this visual approach to the mountain. You're flying this way. And it didn't matter whether you were in a little airplane or a huge transport, 747. I was in an MD-11 when I did this. You'd fly right straight to this point here. But there was what they called a localizer, so the runway was like right here. But there was no approach to the runway given bad weather conditions. And so you couldn't just fly up and make a turn like normal, because they didn't want you in this zone right here. This was a no-go zone. Don't go in that zone there. And so what they did was they had you fly to this target, and you'd be looking over to the right, and also watching for the needle. You had a gauge on the instrument panel with a needle, and it would swing kind of left, and then it would swing right. And just as it approached center, because there was what they called a localizer, and a glide slope came off of here, your gauge would center up when you got to this point right here. You'd make a right turn, and then you'd fly down to the runway. Well, Kai-Tak was like right in the middle of town, right in the middle of this area. So Macau was there, and Hong Kong, and what's the other town right down there? You know? I forget what it is. At any rate, that's how you made that approach. Well, more often than not, as it worked out, there was always a big cloud right here, right? And so you'd be flying along, and the pilots would get really quiet. They'd be sitting there watching this thing, and if all of a sudden that needle swung that way, what you were supposed to do was make a hard right turn and go in anyway. Right? Well, as soon as you did that, even if there was no cloud there was always a cloud here, right? And it was always pouring rain. And that's like January and February. It's like terrible weather there. So you had this, then you had to go through this. So you had a localizer and a glide slope. So the glide slope tells you where you are this way relative to the airport. And the localizer tells you where you are this way relative to the airport. So it is conceivable that you would fly through, not continually through, this stuff, but you would fly through it. Could be 15, 20, 30 seconds, and that's a lot of water going through one of those engines. Now, the altitude these things fly at, you're above the clouds most of the time. You're above the weather, so that isn't a big issue. But once you get down here, so now you've got reduced throttles here because you're on approach. The airplane's headed downhill, and now you're flying through these what they call squalls. The rain squalls is what they are, and you go through those rain squalls. And it is, honest to God, you never seen it rain so hard in your whole damn life. How many ever been on a monsoon? Southeast Asia. So you know what I'm talking about, right? I mean, it just looks like somebody just unzipped a bag of water. Honest to God, you can't see that door. Big drops too. Yeah, it feels like it's hitting you, so it's hitting you with marbles. So it's pretty impressive. Until, I mean, you just say, "Oh, this guy's full of shit." But wait till you're there sometime.
I bet there's a video on it.
Probably is. We ain't gonna see it.
So what happens if
Right.
the water ingested by the engine? Does it damage? I mean,
So the big turbofan engines tend to throw the water out.
it just deflects a little bit. So
Yeah, centrifugal force throws the water out and then down the bypass here, which goes around the core of the engine.
Yeah.
So there's still a certain amount of it goes through the core of the engine or the gas producer.
Mhm.
And that, you don't want too much water in the gas producer because then what happens? You're gonna flame out, right? So, and that's the biggest thing that happens. This also happens with volcanic ash. So volcanic ash will travel hundreds of miles sometimes, and so they have to reroute air traffic control. Whoever's in charge of that airspace will reroute the traffic to go around where they see the volcanic ash is, and then they kind of know where it is from satellite photos, but also they use pilot reports to see where it is because they don't want those airplanes flying through it. The ash itself will slightly degrade the shape of the airfoils in the engine. But more than that, it's the ash itself will choke the engine from air because it's so thick. It just actually displaces the air. Okay, so you all heard about the miracle on the Hudson, right? The U.S. Airways that hit the flock of geese. Have you ever seen a goose? A wild
Jake
goose?
has.
Jake Yeah, Jake
Oh.
Yeah. Tell us your story.
Tell
Tell us your story. Everybody's got a tail. No, you don't have to. So geese have a wingspan, some of them up to 12 feet. And 12 feet is pretty long. And they weigh, a goose can weigh 25, 30, 40 pounds sometimes. And these things are like flying tanks. And these things are only supposed to ingest air, not a boulder. So, but they fly. How many of you from back east ever seen the migration of geese? Any of you? 2, 3, 4 of you. Okay, so geese. Tell me if I'm wrong. So geese, when they fly together, they're flocks, bees, right? Flying bees together, and there could be 100 of them in that formation. Most often it's 25, 30, something like that. So when you hit a flock of geese, you know you hit something. I mean, it's like hitting a concrete wall. So this guy is taking off out of New York, and they set up the flight path of the airplane, and they kind of got their head down because they're monitoring the instruments, and they're kind of watching for other traffic. But all of a sudden, here comes this flock of geese. Now, the closing speed on a flock of geese, because fleet geese, they fly 35, 40 miles an hour when they're at altitude, but down low, they don't fly so fast. But this thing, and the geese were going opposite directions, so the closing speed was fairly high. So they lost the geese in the haze. They knew there were geese out there, and they lost the geese in the haze, and they ended up whacking these things. So they figured, so here's a picture of the airplane after it was brought up out of the river. So the windshield's been smashed. You can see up here at the top, it's knocked the paint right off the windshield. Right? So this has done a significant amount of damage to the airplane. So this guy's flying this airplane. He's a friend of this woman who used to be my girlfriend, and so I met him. I don't know him, I don't get to know him anymore. But Sullenberger and Stiles, these two characters flew this airplane with busted windshields. So that's not a smile on the front there, they've got the radio on. It's not a happy face airplane anymore. But every one of those red marks is where a goose hit the aircraft and caused some structural damage to the aircraft, right? So so these guys are flying this thing. Not only did they land it in the river and keep it upright, they couldn't see where the hell they were going. Right? They couldn't see what the hell was going on outside. They were on instruments. This is the engine panel here. Both engine number 1 and number 2. If you look up at the top up there, those are the fire buttons, and they were deployed. This thing's we emptied the water out of this thing. This is as they emptied it out. So the 2 fire agents were deployed in those engines. They got fire lights, so they deployed those. And so there's the here's the engines here. And I'll show you what happens when you hit a goose. So the geese were bouncing off of everything in there. So you can see from the inlet, you can see up around the top left side up there, you can see that liner up there which cuts the noise down there. Goose stuff all over everything inside there. That white compound is geese. The blades chop up the geese pretty good, but geese have pretty big bones. You know, they're hollow, but they've right, Jake? Big bones. Yeah. So you know, the wing bone is like the size of your wrist. That's how big these guys are, right? So the fan itself, these are 2 CFM 56s, not particularly large fans, but it's a fan that an engine that's on a lot of airplanes, 737s, 757s and such. These are on small Airbuses, baby buses, the whole thing. So so this thing did a pretty good job of grinding things up. It torqued the blades a little bit, kind of white goose stuff on the blades here, down the sides. But it's when you start looking inside what happened, right? So the geese are kind of flailing around in there. Well, they were being flailed. And so behind down here, right in this area here, and you can still see little pieces of geese there. But this is the inlet guide vane here, and this goes to the compressor, to the core of the engine. All right, let's go a little bit further. So the fan blades are pretty tough. So now you can see what happened to the inlet guide vanes here. So it's not the inlet guide vanes off. So that's caused a degradation of the airflow. Back here, the first stage compressor blades are all gone. But this is the second stator vane right here. Right. So it's been knocked cuckoo. And if you look down in there further, it might be a little bit hard to see in this picture. But down inside, most of the rest of this stuff has been knocked out. Anything that's movable down in there has been knocked out. The blades have been taken right off the compressor. Okay, there's a better one there. See, it's all busted in there. Now you can imagine when you've got turbulent airflow going through this compressor, it just doesn't want to run. So an attempt to relight this, which is what they tried to do, one of them was flying and the other one was trying to relight, it just wasn't going to relight because it wasn't moving any air through the engine. This engine was killed. It was killed. There was nothing left for this engine. Okay. Now, when you do the blend job for me, I like those guys too, and I don't get to know them anymore. Okay, so there are different areas of the blade will have different tolerances for repair. Now, if you think about the blade, kind of long, it's attached at one end, and it tends to flex, right? So the place that's going to have the most stress is going to be near the base of the blade. The rest of it's going to be like a fishing pole. It's going to have the ability to whip and change position a little bit, but down at the base is where the major stress is going to be, where it's restrained. When you do some blending, and I have all the books here for these fan blades that you're going to be blending, you have to refer to the book. Now, I'll tell you this, is that when you go do your practical exam with the FAA mechanic examiner, who I know, and I have provided him with books and blades. There's a very good chance what you do in your blending project out here is going to be identical to your project. So please pay attention to it when you're doing it, and know how to read that book and interpret, because you could well. There was a kid out there the other day who was taking his practical, and he's sitting there going grinding on the blade, just like you all are going to do, and that was one of his practical exam test questions. So know that while I'm not cheating, I'm not giving you the answers, because you're going to have to interpret it, and he's going to answer the questions. I gave him blades and I gave him books, so know that could very well be one of your practical test questions.
The 10.
What's that?
Mike.
Those 10. Okay, now hub. The hubs are the wheels that the blades are attached to, the shafts, any structural inspections. Most of those can be conducted in the field. We're going to keep going here. We're almost done. And we'll go get some dinner. Now, most of these, if you operate for an airline, they operate under their own engineering certificate with the FAA's approval. They're not necessarily repair stations. But a lot of large operators are what they call MROs. So these are maintenance repair organizations, and they are repair stations in that case. So they do their own work under their engineering release from the FAA, but they will also work on customer input. So you could, if you went to work for American or United or whoever, you could end up working on Mexicana, Tacna. You could end up working for Malaysian. You could end up working for almost anybody, working on small projects as time fillers. Now, any kind of special inspections, as I say, big operators work to their own drummer, but they'll go right straight to the manual when they start working on customer equipment. Let's see where we're at. There should be about none here. Oh, yeah. Now, these are all part of modules. So the compressor is a module. So should an engine get FODed, and it's maybe a light FOD, maybe an operator will opt to remove the compressor, and you can do that on the wing on most aircraft. Pull the compressor out, stick another compressor in. There's a simple logbook entry. You carry the time forward. Each module has its own logbook. Now, sometimes you have to take some things apart and you get in kind of heavy, but a lot of times they'll do this on the wing. For big engines, small engines, you might just as well pull it right back out of the aircraft. It kind of depends on the situation. But know that sometimes you have to take the thing apart to do a proper inspection. X-ray inspections on rotors, for instance, you may have to take all the plumbing off the outside so it doesn't confuse the X-ray inspection. What they'll do is they'll put a radioactive pill inside the engine and then expose it to film on the outside of the engine. But you can't have all those lines and wires running on the outside of the engine, so you may have to strip back some of what they call a QEC. Anybody know what QEC is? QEC, so you have a basic engine. God, I love that airplane. It's not even open, let me close it, it's scared to me. So it's QEC, put this in your vocabulary. QEC, I'm not going to write it up there, it's quick engine change. QEC, quick engine change. Now what it is, it's all the stuff that is not the basic engine. So it could be pumps, generators, could be the wiring that supports those things, could be extra bleed valves, ducting, the ducting to run the starters, all of that stuff. It's a lot of little bits and pieces of stuff And almost every one of those different systems has different hardware for it. So if you're directed to strip the QEC, make sure you maintain control of that stuff. You don't want to be dropping it on the ground, because a lot of times, as I say, there are special nuts and bolts, washers. Sometimes it's shimmed. There's special prerequisites for installing this stuff. So the basic engine is pretty much there, but what they do is they build these engines up to a position. So if you have an engine number 1 or you have an engine number 2, you're going to put different things on it in different places. Maybe both the hydraulic pumps are inboard on the engines. So that creates another little problem. So the left engine is going to be inboard. Right engine is going to be inboard. So all this stuff has to be reversed. Sometimes you have a thrust reverser that has to be clocked one way or the other. You build it to the position that the engine's going to be operated in, which further complicates things. But most often an airline, big operator, is going to have engines in a pool or they're ready to change. And if you have a problem with an engine, they'll pull one out of the pool that's already set up and has the proper QEC on it. So the QEC is all the nuts and bolts and the loose stuff and all the ductwork, electrical wiring, all that kind of stuff. Okay. So you guys learned some shit here today. You guys learned some stuff. Okay. And if you get in the shop, QEC work is kind of fun once you get onto it. It's a lot of little nuts and bolts and pieces. It's nice, clean work. You work in the back room, so you don't have the rain running down the back of your neck and that kind of stuff. And it's not a bad job, actually. You kind of turn your radio up and cruise away and build up an engine. You get that done, you get another engine out. I was at Delta last summer with Mark, and the QEC shop there, it was like a heavenly little place. They had a popcorn machine and a little toaster oven. Those guys were set, let me tell you.
Nice lunch room.
All right, what I just said there, sometimes it's also common to pull the compressor out to repair. And again, a module is going to have its own logbook. It's going to document the time and cycles on that part. So if you pull a compressor out, it goes back to the shop, carries those time and cycles with it. And when it comes back out, it'll go back into a pool, and they may put it in something else, or they may assemble another engine around that thing. But then that logbook for that module becomes part of the engine logbook set. So the documents are pretty darn important. Anytime there's a inspection made, if you do a boroscopic inspection on a compressor, that's entered into the module logbook, also the aircraft logbook. Okay, pretty good. You guys learn anything tonight? I think you
Shit
probably
ton of
did,
stuff.
whether you realize it or not. So the compressor is kind of an important thing. We'll go into the diffuser and the combustion section next week, and we'll keep thrashing away. So if you want, go get yourself some dinner. Be back about 10 after 8, and we'll get started outside.